Organic chemistry is a captivating dance of molecules where the creation of new compounds takes center stage. Yet the synthesis of these intricate structures is only half the battle. To truly understand and utilize these organic compounds, we need them in their purest form. That's where the magic of purification techniques comes in. Imagine baking a cake and finding bits of eggshell in it. Not very appetizing, right? Similarly, impurities in organic compounds can muddle their properties and hinder their use in various applications. Whether it's developing life-saving drugs or creating cutting-edge materials, purity is paramount. Purification techniques help us separate the wheat from the chaff, isolating our desired compound from unwanted byproducts and impurities. These techniques are the unsung heroes of the organic chemistry lab, ensuring that our final products are pristine and ready for their intended purpose. From the elegant simplicity of crystallization to the sophisticated power of chromatography, each technique offers a unique way to achieve purity. And just like a chef needs to master various cooking methods, an organic chemist must be well versed in these separation techniques to excel in their craft. Crystallization stands as a cornerstone technique in the realm of organic chemistry, renowned for its elegance and effectiveness in purifying solid compounds. This method harnesses the principle of solubility, exploiting the fact that the solubility of most solids increases with temperature. Picture a saturated solution, a dance floor where no more solute can dissolve at a given temperature. As the solution cools, the dance floor shrinks, forcing the solute out of the solution, where it crystallizes into a pure form. Impurities, often present in smaller amounts, remain dissolved, leaving us with sparkling, purified crystals. The process is relatively straightforward. First, we dissolve our impure compound in a suitable hot solvent, creating that saturated dance floor. Next, we slowly cool the solution, encouraging our desired compound to crystallize out, leaving impurities behind. Finally, we isolate the pure crystals by filtration, washing away any lingering impurities. Consider the example of purifying sugar in a sugar refinery. Raw sugar, often brown and laden with impurities, is dissolved in water at high temperatures. As the solution cools, pure sugar crystallizes out, leaving behind impurities like molasses. The result? Pristine white sugar crystals ready for our tables. Sublimation, a fascinating phenomenon, offers a direct route from solid to gas, bypassing the liquid phase altogether. This technique proves particularly useful for purifying compounds that readily sublime, transitioning from solid to gas upon heating, while leaving non-volatile impurities behind. Imagine dry ice, solid carbon dioxide, vanishing into thin air without a trace of liquid. This is sublimation in action. The driving force behind this transformation is the vapor pressure of the solid, which exceeds the surrounding atmospheric pressure at certain temperatures, allowing the solid to vaporize directly. Sublimation finds applications in various fields. In forensic science, it helps analyze dyes and inks by separating their components based on their sublimation points. In the pharmaceutical industry, it plays a crucial role in purifying heat-sensitive drugs, preserving their potency and effectiveness. Camphor, a waxy solid with a pungent odor, exemplifies a compound purified through sublimation. When heated gently, camphor readily sublimes, leaving behind any non-volatile impurities. The purified camphor vapor then deposits onto a cool surface, yielding pure crystalline camphor. Distillation, a cornerstone technique in both laboratory and industrial settings, exploits differences in boiling points to separate liquid mixtures. This method hinges on the principle of vapor pressure, the tendency of a liquid to evaporate. Liquids with higher vapor pressures boil at lower temperatures, allowing us to selectively vaporize and collect them. Imagine a mixture of water and alcohol. Water boils at 100 degrees Celsius, while alcohol boils at a lower temperature of around 78 degrees Celsius. By heating this mixture, the alcohol vaporizes first, leaving the water behind. We then condense this vapor back into liquid form, effectively separating the alcohol from water. Distillation comes in various flavors, each tailored to specific separation challenges. Simple distillation is ideal for separating liquids with significantly different boiling points, at least a 25 degrees Celsius difference. Fractional distillation employs a fractionating column to separate liquids with closer boiling points, providing a larger surface area for repeated vaporization and condensation cycles. Vacuum distillation lowers the boiling points of liquids by reducing the pressure, proving invaluable for separating heat-sensitive compounds. Steam distillation uses steam to vaporize volatile compounds immiscible with water, often employed to extract essential oils from plants. Azeotropic distillation breaks azeotropes, mixtures that boil at a constant temperature, by introducing a third component that alters the relative volatilities of the original components. Distillation finds widespread use in various industries, from refining crude oil into gasoline and other fuels to producing alcoholic beverages like whiskey and vodka. Distillation plays a pivotal role in shaping our world. Differential extraction, a technique based on solubility differences, allows us to selectively isolate a desired compound from a mixture using two immiscible solvents. Imagine shaking a bottle of oil and water. The two liquids remain separate, each harboring different affinities for specific solutes. This principle forms the bedrock of differential extraction. We exploit the fact that a particular compound may dissolve preferentially in one solvent over another. By carefully selecting our solvents, we can coax our desired compound into one layer while leaving impurities behind in the other. Consider a mixture of benzoic acid, aniline, and naphthalene. Benzoic acid, an organic acid, readily dissolves in a basic aqueous solution, forming a water-soluble salt. Aniline, an organic base, behaves similarly when treated with an acidic aqueous solution. Naphthalene, however, remains stubbornly insoluble in both acidic and basic water. By employing a series of extractions with acidic and basic aqueous solutions, followed by extractions with an organic solvent, we can neatly separate these three compounds. Benzoic acid resides in the basic aqueous layer, aniline finds its home in the acidic aqueous layer, and naphthalene remains in the organic layer. Differential extraction proves invaluable in various applications. In pharmaceutical industries, it helps isolate and purify active pharmaceutical ingredients from complex mixtures. In environmental science, it aids in analyzing pollutants in water and soil samples. Chromatography, a powerful and versatile separation technique, reigns supreme in analytical chemistry, allowing us to separate, identify, and quantify components within a mixture. This technique hinges on the differential partitioning of analytes between a stationary phase and a mobile phase. Imagine a racetrack with runners of varying speeds. Similarly, in chromatography, components in a mixture traverse a stationary phase at different rates depending on their affinity for the stationary and mobile phases. This differential migration leads to separation. Chromatography encompasses a diverse array of techniques, each tailored to specific separation challenges. Paper chromatography employs paper as the stationary phase and a solvent as the mobile phase, commonly used for separating inks and dyes. Thin layer chromatography, or TLC, utilizes a thin layer of adsorbent material on a glass or plastic plate as the stationary phase and a solvent as the mobile phase, providing a quick and efficient means for analyzing mixtures. Column chromatography employs a packed column as the stationary phase and a solvent as the mobile phase, offering greater separation power for complex mixtures. Gas chromatography, or GC, utilizes an inert gas as the mobile phase and a liquid or solid stationary phase, ideal for separating volatile compounds. High-performance liquid chromatography, or HPLC, employs a high-pressure pump to force a solvent through a packed column, providing superior resolution and sensitivity for analyzing a wide range of compounds. Chromatography finds widespread use in diverse fields. In pharmaceutical analysis, it helps identify and quantify drug substances and impurities. In environmental monitoring, it aids in detecting and quantifying pollutants in air, water, and soil samples. Purification techniques stand as the unsung heroes of modern science, underpinning advancements in medicine, materials science, environmental science, and beyond. These techniques provide the foundation for obtaining pure compounds, essential for understanding their properties and unlocking their full potential. In the realm of pharmaceuticals, purification techniques ensure the safety and efficacy of life-saving drugs. From isolating active pharmaceutical ingredients to removing harmful impurities, these techniques play a pivotal role in drug discovery, development, and manufacturing. Materials science relies heavily on purification techniques to create high-purity materials with tailored properties. Whether it's developing advanced polymers for aerospace applications or synthesizing nanomaterials for electronics, purity dictates performance. Environmental science leans on purification techniques to identify, monitor, and remediate pollutants. From analyzing pesticide residues in food to detecting heavy metals in water sources, these techniques safeguard human health and the environment. As we venture further into the 21st century, the demand for pure compounds will only continue to soar. Purification techniques, with their ever-evolving sophistication, will remain indispensable tools, driving innovation and shaping the world around us.